Welcome to SciSense, where we unwrap scientific research, because science should not be a puzzle.
Welcome to the SciSense podcast. I am Sarah, and I am here with Mike. Today we are diving into a really clever piece of chemistry that was just published in JACS, the Journal of the American Chemical Society, by Wen Zhang, Yuli He, and colleagues at China Pharmaceutical University in Nanjing. Mike, this paper is about getting rid of a toxic gas that chemists have been forced to use for decades. What is the story here?
So the paper describes a new way to build a type of molecule called a ketone. Ketones are incredibly important in drug design. They show up in all sorts of medications, but traditionally, one of the best ways to make certain ketones involves using carbon monoxide gas, which is the same gas that kills people in house fires and from faulty heaters. It is colorless, odorless, and extremely dangerous.
Right. Carbon monoxide is the one they call the silent killer.
Exactly. And in a chemistry lab, using CO means you need specialized high-pressure equipment, gas detectors, fume hoods, and rigorous safety protocols. Many labs around the world, especially in developing countries, simply do not have that infrastructure. So entire categories of chemical reactions have been off limits to them.
So what did these researchers figure out?
They found a way to use something called an acyl chloride instead of carbon monoxide. An acyl chloride is a solid or liquid reagent that you can weigh out on a bench. It is much easier and safer to handle. And here is the clever part. The acyl chloride does double duty. It provides both the acyl group, which is the piece that would normally come from CO, and the carbon fragment, all in one molecule. So you are replacing a toxic gas with a bench-stable reagent that actually does more work.
That sounds like a win on multiple levels. But there is another dimension to this paper, right? It is not just about replacing CO. It is about making molecules with a specific handedness.
Yes, and this is where it gets really fascinating. Let me explain chirality, which is the technical term for molecular handedness. Hold up your two hands in front of you. They are mirror images of each other, right? But you cannot stack them perfectly on top of one another. Your left hand and your right hand are not identical. They are non-superimposable mirror images.
Like how a left glove does not fit on your right hand.
Perfect analogy. Molecules can be the same way. Two molecules can have the exact same atoms connected in the exact same order, but arranged in three-dimensional space as mirror images. We call these enantiomers, and here is why it matters enormously for medicine. Your body is itself chiral. Your proteins, your receptors, your enzymes, they are all handed. So when a drug molecule enters your body, its handedness determines how it interacts with everything.
So one mirror form might work as a medicine and the other might not?
Or worse, the other might be actively harmful. The most famous example is thalidomide in the 1950s. One enantiomer treated morning sickness effectively. The other enantiomer caused devastating birth defects. Same chemical formula, same atoms, just a different three-dimensional arrangement. That tragedy changed pharmaceutical regulation forever. Now, drug companies must control which mirror form they produce.
Which brings us back to this paper. How does the nickel catalyst control the handedness?
The researchers paired the nickel with what is called a chiral ligand. Think of it as a molecular glove that fits around the nickel atom and creates an asymmetric environment. When the acyl chloride comes in and reacts with the nickel, a process called oxidative addition, the chiral ligand guides exactly how the subsequent bond-forming steps happen. It is like a molecular assembly line where the tools themselves are handed, so the products come out with a specific handedness.
And they got very high selectivity?
Up to 97% enantiomeric excess, which means out of every 100 product molecules, about 98 or 99 are the desired mirror form, and only one or two are the other. That is excellent for synthetic chemistry.
Now, why nickel specifically? Why not use palladium, which is the workhorse catalyst for a lot of carbon-carbon bond-forming chemistry?
Great question. First, there is the cost factor. Nickel costs about $15 per kilogram. Palladium costs about $30,000 per kilogram. That is a 2,000-fold difference. At manufacturing scale, that matters enormously. But beyond cost, nickel has unique electronic properties. It can access multiple oxidation states, moving between nickel 0, nickel 1, nickel 2, and even nickel 3. This versatility allows it to handle the oxidative addition with acyl chlorides in ways that palladium sometimes struggles with. Nickel is reactive enough to break the carbon-chlorine bond in the acyl chloride, yet controllable enough to be steered by the chiral ligand.
So nickel is not just a cheaper substitute. It actually brings something unique to the table.
Precisely. And the substrate scope is impressively broad. The reaction works with many different types of alkenes and acyl chlorides, including ones that carry functional groups commonly found in drug molecules, things like halogens, ethers, and nitrogen containing groups. That functional group tolerance is critical because it means medicinal chemists can apply this method directly to the kinds of complex molecules they actually work with.
What about the products themselves? What can you do with these enantio-enriched ketones?
Ketones are incredibly versatile building blocks. You can convert them into alcohols, amines, or more complex structures through well-established chemistry. Many pharmaceutical intermediates are ketones or are derived from ketones. So having a direct, safe, enantioselective route to these compounds removes a real bottleneck in drug discovery. You are essentially giving medicinal chemists a new, safer tool for building the chiral centers that are present in the majority of modern drugs.
So to sum this up, we have a reaction that replaces a toxic gas with a safe bench reagent, uses an inexpensive earth-abundant metal instead of a precious one, and controls the three-dimensional handedness of the product with near-perfect precision. That is a lot of problems solved in one paper.
It really is. And I think the broader principle might be even more important than the specific reaction. The idea that you can design bifunctional reagents to replace hazardous gaseous feedstocks in metal-catalyzed reactions, that is a concept that could be applied to many other transformations. We could see a gradual elimination of carbon monoxide from the synthetic chemist's toolkit over the coming years. Combined with the shift from precious metals to earth-abundant ones like nickel, this points toward a future of pharmaceutical chemistry that is simultaneously safer, cheaper, and more accessible to researchers worldwide.
That is a fantastic vision. Safer chemistry, cheaper chemistry, and chemistry that more people around the world can actually do. Thank you for breaking this one down, Mike.
My pleasure, Sarah. Nickel is having quite a moment in catalysis research, and I think we will be hearing a lot more about it.
Thanks for listening to SciSense. Share it with a friend. See you next time.